Hello to all. I am Dr. K.Sinha, Professor of Chemistry. Today I am going to discuss tips for solving numericals. Tips for solving numerical problems based on chemical thermodynamics. Already I have finished the entire chapter and reviewed also. I have reviewed also and finished the entire chapter. Complete thermodynamics I have finished and also I have reviewed. Now I am going to discuss tips for solving numerical problems based on chemical thermodynamics. Now I am briefing tips for solving numerical problems. First, Joule's relationship between mechanical work done, that is the W, and heat produced, that is H, that is equal to how both are related, W and H. W means work done and H means heat produced, enthalpy. How both are related? Then W is directly proportional to H. W is directly proportional to H, or W is equal to JH, where J is called mechanical equivalent of heat. J is called mechanical equivalent of heat. Its value is J is equal to 4.184 into 10 to the power 7 ergs. That is equal to 4.184 joules. J you can write in terms of ergs and also in terms of joules. Relation you should remember. J is equal to 4.184 into 10 to the power 7 ergs. That is equal to 4.184 joules. Thus, work done when 1 calorie of heat is produced, that is equal to 4.184 joule. This is the important relation. Work done when 1 calorie of heat is produced, that is equal to 4.184 joules. Second, work done by a gas for expansion from volume V1 to volume V2 against a constant external pressure is W is equal to P into in bracket V2 minus V1. V2 minus V1, P into change in pressure, P into change in pressure, that is W is equal to P into inside the bracket V2 minus V1, that is equal to P into delta V. Now third important point, according to first law of thermodynamics, delta E is equal to Q plus W. Delta E is equal to Q plus W, where Q is the heat absorbed by the system and W is the work done on the system. Work done on the system. Correct? Delta E is equal to Q plus W, first law of thermodynamics, where Q is equal to heat absorbed by the system and W is the work done on the system. Next point, that is related to sign convention. Sign convention for delta E, Q and W. This concept is very important while solving the numericals. If work is done on the system, already I have discussed. Now just as a tips I am telling you. If work is done on the system, W is positive. If work is done by the system, W is negative. If heat is absorbed by the system, Q is positive. If heat is given out by the system, Q is negative. If heat is given out by the system, Q is negative. If energy is absorbed by the system, that is the internal energy increases, then delta E is positive. Very, very important. If energy is absorbed by the system, then obviously energy will increase. That is the internal energy increases. That time delta E is positive. If energy is released, means less. If energy is released, that is the internal energy of the system decreases, it means delta E is negative because it is going outside. That's why delta E value will decrease. That is a delta E is negative. Now here I want to clear that two relations are there. A student generally gets confused. First, heat of reaction or enthalpy change of reaction. Then it has two relations. First, that is I told you, product minus reactant. Products minus reactants means heat of formation, summation of standard heat of formation of products minus summation of heat of products, standard heat of products. Standard heat, here you have to product minus reactant you have to do, keep in mind. Then heat, both are heat of formation of product minus heat of formation of reactant. But heat of product, that is standard, 0 subscript. Then delta, summation of delta H subscript 0 F means standard hydrogen, not hydrogen, heat of formation. Delta H means change. That a small f means formation. Then standard heat of formation of products, all you add. That's why sign of summation minus again sign of summation, standard heat of formation of reactants, product minus reactant. Now second, where student gets confused, if heat of reaction is in term of bond energy, then it will be reverse, reactant minus product. Keep in mind, in term of bond energy, heat of reaction, change of heat of reaction is equal to now reactants minus products, means summation of bond energy. In terms of bond energy I am talking about, summation of bond energies of reactants minus summation of bond energies of products. Correct? Then this is the relation. Then both are reverse way. Bond energy, if in term of bond, we want to tell in terms of bond energy, then reactant minus product. But if you want to tell in the term of, you can say this thing, heat of formation, then that time you have to tell product minus reactant. means standard heat of formation of product minus standard heat of formation of reactants. Standard heat of formation of reactants. Correct? Generally product minus reactant. Only in this case, in terms of bond energy, reactant minus product. Question is asked. Now next relation, already you know, enthalpy, that is the H is equal to E plus PV, and enthalpy change is equal to delta H is equal to delta E plus P into delta V. All these parameters HE you write in the term of delta. Then H is equal to E plus P into B. Then here H will change, E will change, and V will change. Then the term which will change, you write a delta. Then delta H is equal to delta E plus P into delta V, because in case of enthalpy, P will be constant. Now heat capacity. Last class I have discussed heat capacity. Then heat capacity C is equal to Q upon T2 minus T1. Q upon T2 minus T1, where Q is the heat absorbed to raise the temperature from T1 to T2. Now Cv is equal to, means heat capacity at constant volume, Cv is equal to del E upon del T at constant B. Already I told you, Cv means volume is constant, correct? Or for internal energy, always V will be constant, do you remember? And for enthalpy, P will be constant, pressure. Then Cv is equal to del E upon del T at constant pressure, correct? Cv is equal to del E upon del T, in bracket down you write a small b, means constant volume. And Cp, in simple way, delta H upon delta T at constant P pressure, correct? Cp is equal to delta H upon delta T in bracket at constant pressure. And next point, already you know, I have discussed Cp minus Cv is equal to R. Actually, I am giving tips to solve the numerical problems. Now next, work done in isothermal reversible expansion. Expression for work done in isothermal reversible expansion. Then W is equal to, because expansion is there, then volume will be there, you remember, V1 to V2, less to more. Then W is equal to minus 2.303 nRT log V2 upon V1. Last class I have discussed. Minus, why minus? Because system is doing work. Hence, work done will be negative. Then W is equal to minus 2.303 nRT log V2 upon V1. That also you can write, that is equal to, in terms of pressure, Boyle's law will use, then you know that both pressure and volumes are related, inversely proportional. Hence, in the place of volume you write P, and for the 2 you write 1, and for the 1 you write 2, because it is inversely proportional. Pressure and volume both are inversely proportional. Hence for the V volume, you write P first for both. In the place of V you write P, and for the 2 you write 1, and for the 1 you write 2. Means W is equal to, in terms of pressure, minus 2.303 nRT log P1 upon P2. P1 upon P2, because for the work expansion, V2 upon V1 was there. Then now it became P1 upon P2, correct? Then W is equal to minus 2.303 nRT log P1 upon P2. This is maximum work obtained This work is maximum work. This is the maximum work obtained and is represented by W max. W max means maximum. Down you can write. Now next relation, that is for reversible adiabatic expansion. Last class I discussed. For reversible adiabatic expansion, for that PV lambda is equal to constant. Do you remember? Always this question is asked. Numericals are also asked based on this concept. Then here for reversible adiabatic expansion, PV v power lambda, PV lambda is equal to constant. First relation. Second, TV power v power lambda minus 1, lambda not gamma, okay. PV gamma is equal to constant, that is the first relation. Second relation, TV but v power gamma minus 1, that is equal to constant. And third relation, TP and p power 1 minus gamma divided by gamma, 1 minus gamma divided by gamma, that is the power of P pressure. Then Tp 1 minus gamma divided by gamma, that is equal to constant, where gamma is equal to Cp upon Cv. Next, work done during adiabatic expansion of n moles of an ideal gas. Here two conditions you are putting. Gas is ideal, and second, that is for n moles. Then work done during adiabatic expansion for n moles of an ideal gas, that is equal to n into Cv in bracket T2 minus T1, NCV T2 minus T1. Correct? N into Cv in bracket T2 minus T1. If T1 and T2 value are knowing, and if Cv value are knowing, and number of moles you are knowing, then work you can calculate. Work done during adiabatic expansion of n moles of an ideal gas is equal to n into Cv in bracket T2 minus T1. Here adiabatic expansion means Q is equal to 0, no change of heat. Now next relation, that also I have discussed in the last class, QV, Q at constant volume, that is equal to delta E. You remember, when volume is constant, then you are talking about delta E, means change in internal energy, E. You remember, when V is constant, then you are talking about E at constant volume. Then QV is equal to delta E, and QP, P is constant means you are talking about delta H, change in enthalpy. Then these two relations always remember, QV is equal to delta E and QP is equal to delta H. Now further relation, QP is equal to QV plus delta Ng RT. This also I have discussed in the last class. Derive the equation. QP is equal to QV. Here QP means delta H. Then you know delta H is equal to delta E plus P into delta V. Only on that basis. Or in the place of delta H you are writing QP. In the place of delta E you are writing QV. And for the PV is equal to RT, and for the N you are writing delta N, means number of moles of product minus number of moles of reactant. That's why delta N you are writing, and this is applied for gas. Hence you can write a small g delta N G. Then now you got the relation QP is equal to QB plus delta N G RT, or you can write or you can write delta H is equal to delta E plus delta N RT. Delta N RT. Then this delta N is for gas. Then delta N G you can write a small g. And here delta Ng means Np minus Nr. Np means number of moles of product minus number of moles of reactant. That is a delta N. What is the Kirchhoff's equation? Last class I have discussed. Then delta H2 minus delta H1 divided by T2 minus T1, that is equal to delta Cp. Because H you are using, then obviously pressure will be constant. Then delta H2 minus delta H1 divided by T2 minus T1, that is equal to delta Cp, means heat capacity at constant pressure. And same way delta E2 minus delta E1 divided by T2 minus T1, that is equal to delta Cv, because you are talking about internal energy, then volume will be constant, then it will be Cv, delta Cv. Then delta E2 minus delta E1 divided by T2 minus T1, that is equal to delta Cv. Okay, this I have this relation I told you. Now next relation, that is, this is called Kirchhoff's equation. What I discussed now, Kirchhoff's equation. Question is asked based on this relation. Now enthalpy of combustion. Enthalpy of means delta H. Enthalpy of combustion by bomb calorimeter. Okay, or you can tell heat of combustion. Heat of combustion by bomb calorimeter. Instrument name is bomb, B-O-M-B, bomb, atom bomb, same spelling, bomb calorimeter. Then heat of combustion, that is equal to delta E. Delta E. Then delta E is equal to C into delta T into capital M divided by a small m. Delta E, that is the heat of combustion, is equal to C into delta T, change in temperature, into M, capital M, divided by a small m, where C is equal to heat capacity of the calorimeter. Heat capacity of the calorimeter, that is the C, its value is fixed for instrument. Instrument material will absorb some heat. That's why heat capacity of the calorimeter is considered. Then here C into delta T into capital M divided by a small m. Then C is equal to heat capacity of the calorimeter. Delta T is the rise in temperature, that is a T2 minus T1. And a small m is equal to mass of the substance taken, 1 gram, 2 gram, 3 gram, like that way, a small m. And capital M is the molecular mass of the substance. Whatever substance you will take, what is its molecular mass, correct? Then this relation is also important for calculation of delta E. Delta E or heat capacity, combustion, heat of combustion. Heat of combustion. Also you can tell enthalpy of combustion. Now efficiency of heat engine. Last class I have discussed. Actually now I am briefing all the things, because these are the tips to calculate what? To solve the numericals problems. Now efficiency of heat engine, eta, just like a small n. Okay. Then eta is equal to W divided by Q2, and that is equal to W is equal to T2 minus T1, and Q2, that is equal to T2, means W, work done, will take place due to temperature difference. Temperature difference. more the temperature difference, more the work done. And Q2, that is a heat absorbed at temperature T2. Heat absorbed at a temperature T2. That's why W upon Q2. Then W depends upon T2 minus T1. And Q2 heat absorbed at T2. And so you can write eta is equal to W upon Q2, and that is equal to T2 minus T1 divided by T2. And that is equal to, that is also you can write the T2 minus T1, also you can write Q2 minus Q1. Q2 minus Q1 means Q2 absorbed at T2 temperature, high temperature, and Q1 is the heat rejected at T1. That's why you can write in the place of T2 you can write Q2, in the place of T1 you write Q1. Then Q2 minus Q1 divided by Q2, that is also called eta, that is the efficiency of heat. Then three relation, it is related in three ways. Eta is equal to W, that is the work done, divided by Q2, first relation. Second relation is eta is equal to T2 minus T1 divided by T2. Third relation, that is the eta is equal to Q2 minus Q1 divided by Q2, where Q2 is equal to heat absorbed by the system at temperature T2 of the source. Q1 is equal to heat rejected by the system at temperature T1 of the sink, and W is equal to net work done. Now next point, that is entropy change. Then entropy change is equal to Q reversible divided by time. Q reversible divided by time, that is equal to delta S. Now delta, next things, delta S is entropy, remember. Then delta S of system plus delta S of surrounding, that is equal to greater than equal to 0. You remember, very very important. It is telling about the combination of I can say first and second law of thermodynamics. That is the, you can tell the total energy of the universe is constant, but entropy is changing towards maximum, means more than 0. Correct? Equal to 0 and more than 0. Then here delta S system plus delta S surrounding, that is a greater than equal, greater than and equal both, maybe equal, maybe greater than 0, greater than 0 or equal to 0. Then in one way you can write delta S system plus delta S surrounding, that is equal to greater than 0 or equal to 0. Both sign you can write. Okay, greater than sign and then one line you can draw. It means you are talking about two conditions, two things, that is equal to 0 or greater than 0, where equal to sign refers to reversible process, and sign of greater, it is telling about, it is refers to irreversible process. Irreversible, equal sign, reversible process, greater than sign, irreversible process. Next, that is the entropy change of fusion, delta SF. Delta SF, small f, means fusion. Then delta SF is equal to delta HF, delta HF divided by TF. A small f you can write down everywhere. Then delta SF means change in entropy for fusion, that is equal to change in enthalpy for during fusion divided by TF, heat of temperature of fusion. And also you can write entropy change of evaporation, same way. delta H VAP vaporization divided by TB, because vaporization is related to boiling point. Then that temperature is called TB, and fusion time temperature is called melting point. F you can write TF. Hence delta SF for fusion, that is equal to delta HF. Delta HF means during fusion divided by TF melting point, and delta S vaporization VAP, that is equal to delta H vaporization divided by TB. Now most important relation I am telling you, I have not discussed earlier, but here that relation I am telling you. This is a very very important relation, because many relation you will get by using this formula only. By using this relation or expression, many other relation you will get. Then entropy change of an ideal gas. Entropy change of an ideal gas for 1 mole. What is the relation? Listen carefully. Entropy change of an ideal gas for 1 mole. Delta S is equal to Cv into ln T2 upon T1. There are two terms actually. Two terms you have to add. Then one is related to temperature and the other is related to volume. Both terms you have to add. Now I am telling you, delta S is equal to Cv into ln T2 upon T1 plus R ln V2 upon V1. R ln V2 upon V1 means temperature term and volume term. Both term you have to use. Then entropy change, that is the delta S is equal to Cv, heat capacity at constant volume, into ln, natural logarithm ln, Cv into ln T2 upon T1 plus R ln gas constant, R ln V2 upon V1. Then now this is again equal to this volume you can write in terms of pressure. Same way what I have discussed earlier, because V and P are related inversely. Hence in the place of V2 you write P1. For the V you write P, first thing. Second thing, for the 2 you write 1 and for the 1 you write 2. V2 means P1. For the 2 you are writing now 1 and V1, that is the P2. Hence a new relation you will get. First part will be the same, not a little difference. There it was Cv, now it will become Cp. Cp, delta S is equal to Cp ln T2 upon T1, that is the same. Only in the place of Cv, when you are writing pressure, then there you are writing Cp, you remember. Then delta S is equal to Cp into ln T2 upon T1 plus R ln P1 upon P2. Correct? Then this delta S is related to Cb ln T2 upon T1 plus R ln B2 upon V1, and this is equal to Cp into ln T2 upon T1 plus R ln P1 upon P2. Both are related. This is a very very important relation. And now you have to put some condition, then new relation you will get. Okay, only in this relation what I discussed in that, now you put some condition, like when temperature is constant, that is the isothermal process. At constant temperature, then temperature term will be not there, because temperature is constant, isothermal process. Hence temperature term will be not there. Means first term will be not there. Cv into ln T2 upon T1 will be not there. Then what will be there? Only R ln V2 upon V1 will be there. Then other one more relation was there. There also that first term will be not there. Cp into ln Cp into ln T2 upon T1, that term will be not there because temperature is constant, isothermal process. Then what will remain? Only R ln P1 upon P2 will remain. Then now you can see at constant temperature you got relation, new relation, delta S is equal to R ln V2 upon V1, that is equal to R ln P1 upon P2 when temperature was constant. That is the isothermal process. Similarly, at constant volume, when volume is constant, that is the isochoric process. Isochoric process. Volume is constant. Then what will happen? Here we can see that when volume is constant, then volume term will be not there. Volume term will be not there. Second term will be not there. R ln V2 upon V1, that term will be not there. Then what will be there? Only Cb ln T2 upon T1 will be there. Means delta S is equal to Cb ln T2 upon T1. And that is equal to other relation was there. Then that will be not there. Why? Because now only temperature term is there. Here only T1, T2 upon T1 is there. Here volume is not there. Then pressure will be not there. Pressure term will be not there because volume term is not there. Then pressure term will be not there. Only temperature will be there. T2 upon T1. Then third relation, that is the at constant volume. When volume is constant, that is the isochoric process. That time delta S is equal to Cb into ln T2 upon T1. And one more relation, when pressure is constant, at constant pressure, that is the isobaric process. Isobaric. Pressure is constant. Then pressure term will be not there. Pressure term will be not there. Then what you will get? When pressure term is not there, then you got delta S. One more thing, sir. When pressure term is not there, then volume term will be also not there. Volume term will be also not there because pressure term is not there. That is, the pressure is constant, then there is no question of volume. Then here that you will get delta S is equal to Cp ln T2 upon T1. Like first one, there it was Cb, now you got Cp, and T2 T1 ln T2 upon T1 is same. Then delta is equal to Cp into ln T2 upon T1, that is at constant pressure. Here in both these two, at constant volume and at constant pressure, there is no term for volume. This is important reason I told you. If pressure is there, then volume term will be there. If volume term is there, pressure term will be there. But now that relation, volume was not there. In second, pressure is not there, constant. That's why volume term is not there. Now next relation I am telling you, free energy. Free energy, that is the G. Then G is equal to H minus Ts. Just like you are remembering always, H is equal to E plus Pv. Always you are remembering. This is becoming common. H is equal to E plus Pv. Very simple way. Always you are remembering. Okay, like that way you should remember this relation also. G is equal to H minus Ts. Because only on this relation you can get many relation. Then this also you consider as a common relation, but very important relation. Both are very important relation. H is equal to E plus Pv and G is equal to H minus Ts. G is free energy, H is enthalpy, T is temperature, S is entropy. Then this you mug up. G is equal to H minus Ts. Then in the term of free energy, in the term of free energy change also you can write, in the place of G you write delta G, in the place of H you write delta H, and T is a constant, leave it like that. And for the S, you write delta S. Then delta G is equal to delta H minus T into delta S. Now, another relation. Delta G is equal to delta G change in free energy. A standard means always subscript 0. Temperature, pressure, what is the standard value, that will be there. At that condition, what is the delta G, that is called a standard. That like 1 atmospheric pressure, temperature will be 273 Kelvin. Then delta G is equal to delta G, standard delta G of product minus standard delta G of reactant. Simple way, product minus reactant. But here, suppose products are 3 products are there, then add all free energy of all 3 products. If 3 are there, if 2 are there, then add 2 free energy, standard free energy for both products. That's why delta term is used. You don't know whether it is a 1 product or 2 product or 3 product. That's why delta standard, you can say, this you have to write summation of standard delta G of products minus summation of standard delta G of reactants. Same way for entropy change, standard entropy change, same way, summation of standard entropy of products minus summation sign of standard this thing, entropy of reactant, product minus reactant, same way like free energy entropy also, entropy of products minus entropy of reactants. Products, that's why summation sign you have to write summation of standard entropy of products minus summation of standard entropy of reactants. Now next relation, that is related to, you can say, sign only. It is very, very important relation. If delta G is negative, then process is, already many times I discussed, if delta G is negative, then process is spontaneous, or you can tell irreversible, one-sided, means forward direction will go by own. And in a reverse way, if delta G is positive, then process is non-spontaneous. Reaction will not take place simply. Correct? Non-spontaneous. You have to put condition for some temperature, pressure, only then reaction will take place. Then if delta G is positive, process is non-spontaneous. And third, if delta G is 0, then process is in equilibrium. Very, very important condition. If delta G value is 0, then reaction will be in equilibrium or process is in equilibrium. And one more relation which already I have discussed, minus delta G is equal to W useful work done, W useful, that is the minus delta G. Minus delta G is equal to W, but that W work done should be useful, W useful. And Clapeyron equation for liquid and vapor equilibrium of liquid and vapor, there actually Clapeyron equation is applied. Correct? For this liquid and vapor equilibrium, that one equation is there, that is called Clapeyron equation. Last class also I have discussed, that is log P2 upon P1, that is equal to delta HV, vaporization delta HV divided by 2.303 R in bracket 1 upon T1 minus 1 upon T2, or you can write T2 minus T1 divided by T1 into T2, After simplification, 1 upon T1 minus 1 upon T2. After simplification, you will get T2 minus T1 divided by T1 into T2. That's why you can write in the term of T2 minus T1 by T1 into T2 also. Then log P2 upon P1 delta HB means enthalpy change at vaporization. Enthalpy change during vaporization divided by 2.303 R into in bracket 1 upon T1 minus 1 upon T2, or you can write T2 minus T1 divided by T1 into T2 anyway. Then log P2 upon P1 is equal to delta HV divided by 2.303 R in bracket T2 minus T1 divided by T1 into T2. This is called Clausius-Clapeyron equation for liquid vapor equilibrium, where P1 and P2 are vapor pressure at temperature T1 and T2 respectively, or you can tell P1 and P2 are the pressure at which the boiling points are T1 and T2 respectively, and delta HB is latent heat of vaporization. Next term is von Topf reaction isotherm. This is also very, very important reaction. Von Topf, V-A-N-T, von Topf, H-O-F-F, von Topf reaction isotherm. That is equal to, already many times I discussed, delta G is equal to standard delta G plus RT ln Kp. Delta G, that is equal to, delta G is equal to standard delta G plus RT ln Kp, or you can write also all you can say now all are positive. Delta G, before delta G no sign is there, it is positive. That is equal to standard delta G. Here also no sign is there, means positive, plus RT ln Kp. Then here all are positive. That's why you can write mathematically, you can write in terms of negative also. Means minus delta G is equal to minus standard delta G minus RT ln Kp. But more correct is in term of minus. Mathematically both have same meaning. But from the chemistry point of view, minus delta G is equal to minus standard delta G minus RT ln Kp. In terms of minus, that is more correct. Why? Because minus delta G is equal to NEF. One relation is there. Minus delta G is equal to NEF. E means E cell. F means Faraday. N means number of electron. Correct. N is equal to number of electron. Then minus delta G is equal to NEF. Means how you can say free energy converts to or related to these things, E cell, volt. How both are related? Then both are related by this relation only. E means you are talking about volt, E cell. That's why, because you have to make a link minus delta G with E, and again here no, minus delta means G means spontaneous. Then in terms of E must be positive. E cell must be positive for a spontaneous reaction, because minus delta G is related to NEF, and here E is positive. Then both are telling about a spontaneous. Minus delta G means spontaneous and E means spontaneous. For that point of view, this is more correct. From chemistry point of view, negative relation is more correct. You can write negative everywhere. Minus delta G is equal to minus standard delta G minus RTLN Kp, where K is equilibrium constant. Kp is equilibrium constant. And again one more relation is there, that is that dg is equal to V into dp minus s into dt. That is for total differential equation. This is actually not a common relation. It is this is a special relation, okay, but this is very useful relation, and particularly for IIT Advanced, this relation you have to use, because numericals will be based on this relation. You remember from thermodynamics this relation is there. dg means a change in, d means here differential actually, that is related to change only. Then dg is equal to V into dp, pressure. V means volume, P means pressure. V into dp means a difference in pressure or differential pressure, minus S into dt. S means entropy and dt means differential temperature. That's why it is also called total differential equation. This relation is also called total differential equation. Then dg is equal to V into dp minus S into dt. Again I am telling you, dg is equal to V into dp minus S into dt. By using many times it will set in your mind, and by using this relation you can derive two relation based on this relation. By using this relation, how? Simply by making constant. Now dg is, you remember dg is equal to V into dp minus S into dt. And now suppose volume is constant. Suppose V is constant, not constant, temperature is constant. First you think, suppose temperature is constant, dt, then dt is constant, then what will happen? S dt term will be not there. S into dt term will be not there, because T is constant, temperature is constant. Then what will remain? dg is equal to V dp. dg is equal to V dp. Second term will be not there, because temperature is constant. Then S into dt term will be not there, that then S into dt, that term will be not there. dg is equal to V dp. Then V is equal to what? dg upon dp. dg upon dp at constant T, that is equal to V, because you got this relation when temperature was constant. That's why you should write del G upon del P at constant P. In bracket you write del G upon del P. In bracket down you write T, that is equal to V. One relation. Second relation, now pressure you make it constant. Pressure. Then V into dp, that will become 0. Correct? V into dp, because pressure is constant, dp will become 0. Then V into 0, that is the 0. Then dg is equal to minus s dt. Then what will remain? dg is equal to minus s dt. Then what will be? Minus s is equal to dg upon dt. dg upon dt is equal to minus s. But this is at constant pressure. Hence del G upon del T at constant P. At constant P, that is equal to minus S. Then this you remember, at constant temperature dg upon dp, that is equal to V. Del G upon del P at constant T is equal to V. And at constant pressure del G upon del T, del G upon del T at constant P is equal to minus S. Then now only in one class, now I have briefed entire relation of this chapter. It will be very easy while solving the numericals and answering the questions. Okay. Now I am stopping only here. Next class again I will discuss some special points which you should know. Thank you.